These are notes for section 12.1 of Calc 3. Always takes a little while for me to set this up. All right, so we're on page 792, 12.1, start of Calc 3, using Stewart's Calculus, 8th edition, early transcendentals. So if we start off with a three-dimensional coordinate system, most of Calc 3 is 3 dimensions. So the first thing we have is the X, Y, and Z coordinate system. As you can see, positive X is considered coming out. Pretend you're coming out of the book, out of the page, is positive, and going back in is negative. And positive Y is considered going to the right, and positive Z is considered going up. Now, at first glance, you might think that's kind of crazy. Why don't we just leave X the way it used to be, going horizontally, Y going vertically, and let Z be the oddball one coming in and out. But there's actually a very good reason for doing it this way, as we shall see later, is because we want the Z to be considered the height. In 2 dimensions, we have Y being the height. And so likewise, we want Z to be the height. Okay, so X is considered coming out, positive X, positive Y is to the right, positive Z is up. This right hand here is just to indicate that it follows a right hand rule. If you start with your right hand and have your fingers going toward the positive X axis and curl your fingers toward the positive Y axis, then your right thumb points in the direction of the positive Z axis. All right, so by having the 3 coordinate axes, you have what's come out to be 8 octants, O-C-T-A-N-T. In 2 dimensions, we have 4 quadrants. So in 3D, we have 8 octants, and I'll be showing that with my own illustration in just a minute. The first octant, as you might guess, is determined where everything is positive, X, Y, and Z are positive. There is no set rule for the other octants, though. So we don't say for sure this is a 2nd octant, 3rd octant, and so on, all the way to the 8th octant. Although I suppose if you had to guess what the 8th octant would be, it would be the octant where all 3 are negative, right? All right, I want you to notice over here also the coordinate planes. In figure 3, you have the XZ plane, the XY plane, and the YZ plane. Okay, I'll normally refer to the XY plane as the plane of the floor. So you can imagine that the floor that you're standing on, I'm assuming if you're standing on the floor, that's the XY plane. Z is equal to 0 there. Okay, and you just proceed by analogy after that. If the XY plane means Z equals 0, then the YZ plane means X is 0, and the XZ plane means Y equals 0. So if you look at the YZ plane, that's what we normally thought of as the XY plane, the plane of, let's say, a piece of paper. Okay, so X is 0 there because you're not going either in or out. Again, the XY plane, what we're normally thinking of as the XY plane, Z is equal to 0. That's the plane of the floor. And you can kind of see the normal XY plane that we're used to. If you imagine this is the origin and positive X is to the right, positive Y is up. So if you kind of turn your body and angle it from way over here, then you see the usual XY plane that we're used to. Okay, and then the XZ plane is Y equals 0 because you're not going anywhere to the left or to the right. Okay, here's a point in space. They're showing you the first octave view, figure 4, the point A, B, C. So it's an ordered triple, and you kind of have to get used to that. We're used to saying ordered pair, X comma Y. Now we have to say ordered triple, X, Y, Z. So there's the point in space A, B, C. Notice it's A in the positive X direction, B in the positive Y direction, and then C units up. Okay, so you go out of the page and to the right and then up. So this would be the point A, B, C, shown right over here. Here's a box, figure 5 on page 793. Okay, so here's the origin, 0, 0, 0. And we kind of have to get used to that also, right? We're used to saying the origin is 0, 0. Now we have to say the origin is 0, 0, 0. And here's a point in space, A, B, C. Okay, so we form a box, and here are the coordinates of all the other vertices of the box. So notice A, 0, 0 is on the x-axis, 0, B, 0 on the y-axis, 0, 0, C on the z-axis. And there's all these other points, right? So that one, and that one, and that one, and so on. Okay. Okay, so for instance, this point right over here, A0C. So you go A units out, you don't go anywhere left to right, and you go C up, and so forth. Okay, here's some pictures. Figure 7, Z equals 3 is a plane. Imagine you start at the origin, you go 3 units up. Okay, and sometimes I can't show it to you because the book is heavy and I ran out of hands. But then you can go anywhere you want in the X direction or the Y direction. So you have a plane. Think of it as like going up to the 3rd floor. You take the elevator in the 3rd floor. Okay, I'm on the 3rd floor, but I can now walk anywhere in the X direction, Y direction. So Z is equal to 3. Here they're trying to show you Y equals 5. That's 5 units to the right from the origin. And then you can go anywhere you want in the X direction, which means in or out of the piece of paper. And you can go anywhere you want in the Z direction. Okay. So notice by analogy, Y equals 5 in R2. So R2 is 2 space, the set of all ordered pairs where X and Y are any real numbers. R3 is a set of all triples, X, Y, and Z, where X, Y, and Z can be any real number. So here Y is equal to 5, but X can move anywhere you want. Now this is also Y equals 5, but not only can X move anywhere you want, but Z can also move anywhere you want. And so you end up with an entire plane, as you can see over here. Okay. All right, so I'll give you my own version of what's going on. So think back to 2 dimensions, and we'll be doing this a lot in our class. We'll refer to what happens in 2 dimensions. So we'll say, oh yeah, this is what happened in 2 dimensions. And now let's just apply that to 3 dimensions. All right, so we know we have an ordered pair, X comma Y in the first quadrant. We have quadrants 1, 2, 3, and 4 in 2 dimensions, 2D. Sometimes we just have a first quadrant view. So we don't want anything negative, or some word problems, right? Don't allow for any negatives. So we just look at the first quadrant. So it's a first quadrant view. So in 2D, 2 dimensions, we know how to analyze the 4 quadrants, right? Quadrant 1, X and Y are both positive. Quadrant 3, X and Y are both negative. Quadrant 2, what? X is negative, Y is positive. And quadrant 4, X is positive, Y is negative. So by analogy in 3 dimensions now, and this is the way that I'll draw my pictures. I'll draw Y and Z horizontal and vertical just as normal. So if you temporarily ignore the X-axis, if you look at the Y-axis, that used to be the X-axis, right? And if you look at the Z-axis, that used to be what we call the Y-axis. And now X, I'm going to draw like so, and you kind of have to imagine you're creating the illusion that this X-axis is walking out. You're really walking out 1, 2, 3, 4, or you're going into the paper 1, 2, 3, 4, and so on. And this is to indicate that you really have right angles. I know if you look at a 2-dimensional figure, you might not think they're right angles, but you have to kind of pretend you're looking at an illusion from the first octant, right? That's a right angle, that's a right angle, that's a right angle. Okay, so here's a point X comma Y comma Z in ordered triple. And sometimes we just want the first octant view where X is greater than 0, Y is greater than 0, Z is greater than 0. And that's analogous to a first quadrant view. Okay, now there is an understanding of the first octant where X, Y, and Z are all positive, but there's no standard for the other octants. So we don't say the second octant is minus, plus, minus, or whatever. Okay, although again, I suppose if you want to refer to the 8th octant, the most logical guess for the 8th octant is where they're all negative. That's not really set in stone, but that seems most logical. So in 3 dimensions, the only octant that we will say for sure is the first octant where X, Y, and Z are positive. Okay, but no set rule on which is octants 2, 3, 4, 5, 6, 7, 8, whether it's minus, plus, minus, or minus, minus, plus, or plus, minus, plus, or whatever. Okay, and what I showed you earlier in the text, so this is a nice little handy summary here. The XY plane means Z is equal to 0. So it's almost like whatever plane you have, it's the other letter that's left out equals 0. So XY plane, Z equals 0. So by that same game, for the XZ plane, what do you think that means? Y is 0. And likewise for the YZ plane, X is 0. And that's getting back to this picture over here. So if you look at the XY plane, the plane of the floor, there's no height. So Z is 0, ground floor. YZ plane, X is 0. That's sort of like the plane of the piece of paper. Okay, you're not going in or out of the paper. So X equals 0. And then you see the XZ plane, that means Y is equal to 0. You're not moving anywhere left or right. Okay. And now let's look at a point on each of the coordinate axes. I showed this to you in the text also, but here's a first octant view. So here's the point x, 0, 0, 0, y, 0, and 0, 0, z. So if a point is on the x-axis, that means y equals 0 and z equals 0. And of course, once you have that, you can proceed by analogy. If you're on the x-axis, the other two letters are 0. So likewise, if you're on the y-axis, the other two letters, x is 0 and z is 0. So if you look at the y-axis, right, you go this way or this way, well, you're not coming in or out of the paper, which means x is 0, and you're not going up or down, so z is 0. Okay, and likewise, if you take a point on the z-axis, both x and y are 0, because if all you do is you go up and down, you're not coming in or out of the paper, so x is 0, and you're not moving left to right, so y is also 0. Okay, and that's a characteristic for x-intercept, y-intercept, z-intercept. If you have an x-intercept, it means y and z are both 0. A y-intercept means x and z are 0, and z-intercept, x and y are 0. And that's by analogy. Think back to your Algebra 1 class, right? If you're in two dimensions, if you had an x-intercept, it was the other letter, y was equal to 0. And likewise, if you had a y-intercept, that means x was equal to 0. Okay, yeah, here's the analogous picture that I have over here, right? So if a point is on the x-axis, y is 0, and if a point is on the y-axis, then x is equal to 0. Okay. All right, then in terms of formulas, this is pretty much just going by analogy from what we did in 2 dimensions. Okay, distance formula. How far is it from one point to another point? Okay, so if you have P1, and I'm on page 795, x1, y1, z1, and point 2, x2, y2, z2, the distance between the points. Just proceed by analogy. The distance formula in 2 dimensions was this, was it not? The square root of x2 minus x1 squared plus y2 minus y1 squared. So what happens in 3 dimensions? Simple, just add on z2 minus z1 squared. Okay, it's the Pythagorean theorem in 3 dimensions. If you're not sure about that, you can show that the Pythagorean theorem does hold. Let's say that the Pythagorean theorem holds for this triangle, and then it would also hold for this triangle, and you get what you want. Okay, so the distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Another way to think of it is this is delta x squared plus delta y squared plus delta z squared, using the language of delta, change in x squared plus change in y squared plus change of z squared. And of course, that does lead us to the formula for the equation of a sphere. Okay, so this is the bottom of 795. So if you have a sphere, equation of a sphere centered at h, k, l, and radius r. Okay, now from your analytic geometry, if you look at this, that's the equation of a circle, right? X minus h squared plus y minus k squared equals r squared. Circle centered at h, k, radius of r. Okay, so now all you do is add the z part. Okay, so you have the equation of a sphere. And by the way, you can put all these on your cheat sheet, your formula sheet. X minus h squared plus y minus k squared plus z minus l squared equals r squared. That's an equation of a sphere, center h, k, l, and radius r. Okay, and if you're centered at the origin, it's simply x squared plus y squared plus z squared equals r squared. And by analogy, if you left off the z part, right, x squared plus y squared equals r squared. Circle, center of the origin, radius of r. Add the next dimension, sphere, right? Sphere, center of the origin, and radius of r. Okay. All right, so now for some of the homework on page 796. Okay, so I'll show you all the problems. In case you don't have the book and you say, I never want to get the book, I will show you key pages. All that. And maybe some more stuff over here, although I don't think, and maybe we don't have to do any of this stuff. But anyway, that's that. Okay, problem 3. Which of the points A, B, and C is closest to the YZ plane which point lies in the XZ plane. Okay, so what does that mean? So here are the given points. The YZ plane means X equals 0. Okay, which one is closest to X equals 0? It really means look at the X coordinates and which has the smallest absolute value. Okay, so this point, -4, 0, 1, that's 4 units away from X equals 0, right? That's 3 units away. That's 2 units away. So that means point C is the closest to the YZ plane, is the closest to X equals 0. It says which one is on the XZ plane? XZ plane means Y equals 0. So that's point A. Okay, number 2, it says describe and sketch the surface represented by X plus Y equals 2. Number 7, X plus Y equals 2. I think the easiest way to do this is start off with what you know. Pretend Z is 0, the XY plane. Okay, so I picked some convenient points, 2, 0, and 0, 2. Right? If I were in just X and Y, 2, 0, 0, 2. So just have Z equals 0, 2, 0, 0, 0, 2, 0. And then all that happens after that is take that line and move it up and down. Right? Move it up to Z equals 1. Move it up to Z equals 2. And go down to Z is -1, -2. So there's my feeble attempt at drawing such a picture. And by the way, don't worry about artwork. I'm a very bad artist. So if you say I can't draw, well, join the club. I don't know how to draw very well either. You will have to do some sketches, but nothing elaborate in our course. Okay, so X plus Y equals 2 is a plane. Okay, think of the line X plus Y equals 2 in 2 dimensions, and it just changes height. Just move it up and down, and you generate a plane. Okay. Number 9, find the length of the sides of the triangle. I'm just using the distance formula 3 times. Okay, so the points were 3, -2, -3, 7, 0, 1, and 1, 2, 1. So this is from P to Q is simply 2 minus 3 squared plus -2 minus 0 squared plus -3 minus 1 squared. Comes out to be 30, square root of 36 or 6, right? It's x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Take the square root of the whole thing. Distance from Q to R. It's basically delta x squared plus delta y squared plus delta z squared, square root of the whole thing. So square root of 7 minus 1 squared plus 0 minus 2 squared plus 1 minus 1 squared, 36 plus 4 plus 0, radical 40, 2 radical 10. And distance from P to R. So from here to here, subtract the x's, subtract the y's, subtract the z's. So square root of 3 minus 1 squared plus -2 minus 2 squared plus -3 minus 1 squared, square root of 4 plus 16 plus 16, square root of 36, which is 6. Okay, so that means I have an isosceles triangle. 2 sides are the same. You do not have a right triangle. If you try to do a squared plus b squared equals c squared, it doesn't work. See, well, this squared is 36. This is 36, that would be 40, so no 2 added to a third, so it's not isosceles. Okay. Okay, 11, how do you determine if points lie in a straight line? Well, if 3 points are in a straight line, okay, then 2 of the distances have to add up to a third, right? So if you point here, here, and here in space, okay, how do you know if you get a straight line or if you end up with a triangle? Well, if you have a straight line, then let's say the distance from here to here plus the distance from here to here should be the distance of the longest parts of the segment, right? So we find the 3 distances. The points they gave me for 11B are D 0, -5, 5, E 1, -2, 4, and F 3, 4, 2. So I find the distance from D to E. Square root of 0 minus 1 squared plus -5 minus a -2 squared plus 5 minus 4 squared. By the way, you can put all these formulas on your formula sheet. So square root of 1 plus -3 squared is 9 plus 1, radical 11. Okay, how far is it from E to F? Square root of 1 minus 3 squared. You probably know it doesn't matter how you subtract. So you went 1 minus 3. Can I go 3 minus 1? Sure. 1 minus 3 is -2. 3 minus 1 is 2. But either way, when you square it, you get 4, right? So 1 minus 3 squared plus -2 minus 4 squared plus 4 minus 2 squared. square root of 4 plus 36 plus 4, radical 44, which is 2 radical 11. Distance from D to F. 0 minus 3 squared is negative 5 minus 4 squared plus 5 minus 2 squared. Square root of negative 3 squared is 9. Negative 9 squared is 81. 3 squared is 9. So radical 99. 99 is 9 times 11. So 3 radical 11. Okay, so I noticed that's radical 11, 2 radical 11, 3 radical 11. So the distance from D to E plus the distance from E to F is equal to the distance from D to F. Therefore, yes, the points are collinear. They do lie in the same straight line. 15, find the equation of a sphere passing through 4, 3, negative 1, and a center 3, 8, 1. So this automatically tells me it's going to be x minus 3 squared plus y minus 8 squared plus z minus 1 squared. And then the radius is just the distance between these 2 points. Okay. All right, so center, radius. So right away, I know it's x minus 3 squared plus y minus 8 squared plus z minus 1 squared is equal to something squared. So the radius is the distance between these is the square root of 3 minus 4 squared plus 8 minus 3 squared plus 1 minus a negative 1 squared. So negative 1 squared is 1, 5 squared is 25, 2 squared is 4. Radius is radical 30. Therefore, the equation is x minus 3 squared plus y minus 8 squared plus z minus 1 squared is equal to radical 30 squared, or 30. Okay. 19, show that the equation represents a sphere and find its center and radius. Okay, so 2x squared plus blah, 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 blah. Okay, so here is the problem. First, I'm going to divide through by 2, divide both sides by 2. That does give me a fraction, but you know, that's the way it goes. X squared plus y squared plus z squared plus equals 4x minus 12z plus a half. Okay, move the 4x over, it'll become a negative 4x. Move the negative 12z over, it'll become positive 12z. And then I complete the square. Remember completing the square? Take half the coefficient of x and square it. Half of negative 4 is negative 2. Square it, you get 4. So plus 4 on both sides. Same thing here. Take half the coefficient of z and square it. Half of 12 is 6. 6 squared is 36. See what happened to the y? I would have to do it with y if they gave me something with a y, but I didn't have any, right? Like if they had 6y, then I'd have to figure out completing the square with that, but no need to. So y is just going to stay y squared. Okay, this factors in x minus 2 squared plus leave y squared alone, then z plus 6 squared, and this comes out to be 40.5, which is 81 over 2. All right, so the center is 2, 0, negative 6. The radius is the square root of 81 over 2, or 9 over radical 2. And you could just leave it like that. Okay, 23. Find equations of the sphere centered at 2, negative 3, 6. Then touch. Now it says that touch. Let's assume that it means it's tangent to each of those planes. Okay, tangent to the xy plane, yz plane, and xz plane. So I'm going to change it to tangent. So xy plane means z equals 0. That means I want the radius to be 6. Okay. If you have 2, negative 3, 6, how can I get tangent to the xy plane? It just barely grazes it if the radius is 6. For the yz plane, that means x equals 0. X is 2 here, so I want the radius to be 2. And then the xz plane means y equals 0. So if y equals 0, then at 2, negative 3, 6, I want the radius to be 3. So all you're doing is changing the radius. So in each case, it's going to be x minus 2 squared plus y minus a minus 3, y plus 3 squared plus z minus 6 squared. So the only thing that changes is the radius. So radius is 6, 36. Here, radius is 2, 4. Here, radius is 3, 9. Okay, so that's all. All right, then finally, we have some problems involving discussion of what things look like in R3. Again, R3 is space, the set of all x, y, and z triples. R2 is the XY plane. So R3 is XYZ space. All right, so for problem number 25, it says X equals 5. So what does X equals 5 look like? So you take the plane of the piece of paper and you walk out 1, 2, 3, 4, 5, and then you can go anywhere you want in Y or Z. So you have a plane parallel to the YZ plane and 5 units in front of it. So X equals 5. It's the YZ plane, which is X equals 0. And then you go 1, 2, 3, 4, 5 out, and then you can go anywhere you want in Y or Z. So that's a description of it. Okay. I guess another way to say it is the set of all points 5, comma, Y, comma, Z. What I'm trying to show you here is 5, comma, Y is a vertical line. Remember, in 2 dimensions, if I just say X equals 5, that's a vertical line because Y can change to whatever it wants. Okay. 5, Y, Z. X has to be 5. So I walk out 5 units. And then Y, which is left and right, can go anywhere. And Z, which is up and down, can go anywhere. All right, so that's what we have there. Okay, 29. 0 less than or equal to Z less than or equal to 6. Well, Z equals 0 is the XY plane. Z equals 6 is 6 units above it. And then you have everything in between. So you have the Z equals 0 plane, the plane Z equals 6, and all the points between them. Okay, where Z is basically the height. Okay, so sometimes I call that an infinite sandwich. Okay, so the bottom of the sandwich is Z equals 0, the top of the sandwich is Z equals 6, and you have everything in between. Okay, or think of Z equals 0 is the 0th floor. Okay, you walk up to the 6th floor, and then you have everything in between. Okay? Where the analogy doesn't quite hold is normally when we go to a building, right, the heights are all integers, like Z equals 0, Z equals 1, 2, 3, 4, 5, 6, 6th floor. But in reality, when you build buildings, of course, you say first floor, second floor. But here, Z can be, 0.5 or pi or E or square root of 2 over 2. Those are all allowed. So you have Z equals 0, Z equals 6, and everything in between. So you have this huge sandwich, infinite sandwich. Okay. Okay, 35. 1 is less than or equal to X squared plus Y squared plus Z squared less than or equal to 5. Okay, if I make this equal, that's our unit sphere. You've heard of unit circle. The unit sphere is centered at the origin and radius of 1. X squared plus Y squared plus Z squared equals 5 has a radius of radical 5. Okay, so you want the spheres centered at the origin with radius 1 and radius radical 5 and all the points between them. So here's my feeble attempt of drawing such a thing. Okay, that inside sphere in 3D is supposed to be the unit ball, unit sphere, X squared plus Y squared plus Z squared equals 1. The outside one has a radius of radical 5, and you want all the points on both spheres and everything in between. You're counting both spheres because you have the line underneath in both cases. Okay, finally for 37. X squared plus Z squared is less than or equal to 9. Okay, now if you were only in the XZ plane, X squared plus Z squared equals 9 is a circle. And then X squared plus Z squared less than or equal to 9, you take all the points that are in between them. All right, now there's no restriction on Y. Okay, so imagine a cylinder, infinitely large cylinder, with a circle X squared plus Z squared equals 9. Okay, circle like this. Okay, X is going in and out, Z is going up and down. And then you change Y. So see, I'm just moving the circle left and right. Okay, so Y is ranging through all the real numbers. So you have the circle and everything in between and all the points also inside. So here's sort of a cross section in the XZ plane, right? We have the XZ plane, you have all the points that are like them. Okay, but you're really turning it like so. Take this picture, turn it on side, and then move it forever left and right. And that's the picture of what you have in this particular case. All right, and what I'll often do is go back and refocus all this, because when I lay the paper down on the floor, it may not be focused, so I'll have to raise it up again. And I know I'm going through this fast, but you can always rewind, fast forward the video as much as you want. So these are just some of the homework problems, and that's typically what I'll do in my lectures. I'll just do problems from the lecture or from the homework, and that's a little bit less homework that you have to do, but it should give you a template as to do the rest of the homework. All right, so this was section 12.1 for Calc 3.